Welcome back, everybody. Today we will be looking at the polar graphs of rose petals and also lemniscate. So the section previous to this, we looked at graphs of limasones or cardioid graphs, is what we call it. So that one we have a general equation which we went by, and that was r is equal to a plus b cosine of theta, or r is equal to a plus b sine of theta. So for the case of the rose petal, which we're going to look at first, has a general form of r is equal to a cosine of b theta. So what happens when you multiply by a factor of a, which usually has to deal with the magnitude, the size of the radius, and also if you have an inside argument inside the trig function, which in this case is going to be b. Now, in the Cartesian version, if you have, like, say, cosine 2 theta, cosine 3 theta, that allows you to adjust the graph so that there is a compression horizontally. But unfortunately, with polar, it is not exactly the same thing, so we can't actually make that assumption. The a value, though, that we can. We just basically say that the radius is going to be increased by a magnitude of whatever the factor of a is going to be. So without further ado, let's go ahead and jump into this just to see how that actually works out. Now, I'm going to go ahead and create a chart as we have been doing so for the last few sessions. We have r, we have theta, and then we have the following. We have 0, 90, 180, 270, and then 360. Now, when I plug those values in to figure out what r is equal to, we're going to get the following. We're going to get 8 multiplied by cosine of 0, which is going to be equal to 8 in this case. When we plug in 90, we're going to get 8 multiplied by the cosine of 180, which is equal to negative 8. Then we have 8 multiplied by the cosine of 360, which will then give us 8. 8 multiplied by the cosine of 270 times 2, so that's 540. That is going to give us negative 8. And finally, 8 multiplied by the cosine of 720, which is going to give us 8 once again. Now, you can see that's a little strange already because we're only getting 8 to negative 8, so that tells me I need a little bit more information to work with. So what we do in the past, as I said, was, okay, let's go ahead and try to use the values of the ends of the quadrant, 0, 90, 180, and 270, and 360, in order to figure out, where are the critical values of the graph. But because of the factor of 2 theta, I think I need to kind of modify that a little bit. Instead of having to just use the multiples of 90s, I need to kind of wedge in between and maybe use the multiples of 45. So that is to say, I need to know what happens at 45 degrees, also 135 degrees, and then also 225 degrees, and then also 315 degrees. Because again, thinking about compression, right? I need those values because when they multiply by 2, that's going to give me something that I actually am looking for. So let's go ahead and see what happens in between then. Let's see, at 45, we are supposed to get 8 multiplied by the cosine of 90, which then gives me the 0. 8 multiplied by cosine of 270 for 135, that's also going to give me 0. 8 multiplied by the cosine of 450, that also gives me 0. And I'm pretty sure at 315, that's also going to give me 0 because that's 8 multiplied by the cosine of 630 degrees. Okay, so those are where the zeros are going to be located. And now we can kind of work with that. All right, so let's go ahead and try to translate everything. From 0 to 45 degrees, we're going to go from a radius of 8 to 0. So we're going to start out at 8 over here, and we're going to go to a radius of 0, which tells me it's the pole. Now remember, we're only looking inside from 45 degree to 0 degree. So that means we're looking at this region right here. Your radius is decreasing, and as your rotation goes counterclockwise, just like on the unit circle, your radius goes from 8 to 0. So to me, that means you're probably going to do something like this right here. Okay, so that right there is going to be kind of like the first part of the curve. And now let's go ahead and think about what happens from 45 to 90. From 45 to 90, you are going to go from a radius of 0 to -8. So that means from here, 45 to 90 degrees. I'm not going to be graphing in that region really, because remember, your radius is negative. So that tells me I'm really graphing in the opposite part, which is over here from 225 to 270. So for that one, let's see first. 90 comma -8, that's the same thing as going in the 270 direction out by 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be somewhere over here. Okay, put it all together once again, as I said. You're going to be graphing normally in this region, but because your radii are negative, so that means you're graphing in the opposite over here direction then. So in the vertical angle part of it. So your curve, you can hopefully see that you start from the origin, and then you're going to go down this way, right? And you're going to curve into that 270 comma 8, or in our graph, 90 comma -8 then. Okay, so that is going to be our second part. Okay, so there we go. Next, after that, we go from 90 to 135 degrees. So that is located over here, right, in quadrant 2. But again, let's see what happens. Because our radii are negative, because it's -8 to 0, then that means we're going to be graphing in the vertical angle part, which is located over here. And that makes sense because remember, you have to start from this point, which is 90 comma -8, and you're going to go back to the pole because at 135 you have 0. So that means you're going to go back to the origin. So graphically, it's going to curl inward like this, and then it's going to go back symmetrically, just like we had before, back into the origin. So here you can see what's happening, hopefully. So this is kind of like a really weird graph because we've never seen anything like this before, and it's definitely not a function because, you know, it fails the vertical line test. Okay, let's keep going. From 135 to 180, we are graphing over here, still in quadrant 2. Your radius is going to go from 0 to +8. So at 180 comma 8, we're going to go out 8 in the 180 direction. So 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be somewhere over here. So graphically, let's see. I will go ahead and spiral outward to probably this point that's over here then. Okay. So that is going to be the first portion of our graph. So that's what it actually looks like then. And again, remember, you have to kind of like, you know, use what's happening in Cartesian to help you out a little bit, but unfortunately you can't depend on everything in Cartesian. In Cartesian, you know, x and y, we have a graph that has a cycle that starts at 180, that starts at 0 and it ends at 180 because of compression. That will be our period. But over here, our period is obviously not 180 degrees because that is not going to be the end of the graph. We still have the other piece from 180 to 360 degrees, so there's still more to actually come. Okay. All right, so let's see here. Oh, by the way, I think it might be nice for me to kind of label some of these a little bit more. Let me go ahead and do the following. So over here, I'm going to go ahead and say for the curve, we start over here, so that's number 1. And then now it goes down this over here, so that's number 2. And then this is going to be number 3, curve number 3. And then this is going to be curve number 4 then. Okay. Actually, it might be good if I use like a darker color because it's not exactly easy to see. So let me go ahead and change it one more time. So here's curve number 1, curve number 2, curve number 3, and then we have curve number 4. So graphically, hopefully you can kind of see where curve number 5 is actually going to end up. And so let's just go ahead and verify just to make sure. For the next part, 180 to 225, you are going to go from a radius of 8 to a radius of 0. So that is located over here. Okay. So here is your radius of 8 going to a radius of 0. So that means you're going to go to the pole. So that means it's going to curl back in back to the origin. So that is going to be our curve number 5. And you can kind of now see where this graph got its name because what I'm creating now looks kind of like a whole bunch of rose petals then. Okay. Next, we go from 225 to 270. So that is going to be this piece over here, right? So 225 to 270. But because your radii are going to be negative, right, because it's going from 0 to -8, we're going to be graphing in the opposite vertical angle direction, which is going to be quadrant 1. So let's see. Let's find that location first. 270 comma -8. So that is going to go up into the 90. And we're going to go 1, 2, 3, 4, 5, 6, 7, 8. So that means it's going to be this point over here. So the rose petal, it looks like it's going to take a turn and it's going to go out this way. Okay, so it's going to curl upward this part. Okay, and you can probably see where it's going to end up then as a result. The next part, which is 270 to 315, so that is going to be in quadrant 4, but because it's negative, we're going to be graphing in quadrant 2, so that is now going to curl back into the origin or the pole. And finally, for the last one, from the pole out into the last point, which is going to be 360 comma 8, so you're going to go back to the original point of where you started. So then that is going to curl this way then as a result. So that is going to be our final graph. And also just labeling the curve petal. So this was supposed to be number 6 over here, number 7, and then finally number 8 over here. So this graph, yeah, it's definitely a lot more difficult than what we've been encountering in the past. And again, note, we don't want to go back into Cartesian, meaning I don't want to take this equation and change it into terms of x and y because it's just going to be really nasty, and we don't want to even bother with that if possible. Okay, so yes, that's going to be our curve then in this case. Okay, so let's take another example so you can see how this actually works out. This time I'm going to go ahead and use a different trig function, which is going to be sine. And I'm also going to change that number inside the argument so that it's sine 3 theta instead of, like, say, sine 2 theta, just to see how that actually works out. Okay, so here we go. Let's see, we have 0 for theta, and then we have r over here. And let's again think about the values of theta that we're going to be using in this problem in comparison to what we did in the past over here, right, in the last problem. Because of the argument of 2 theta, I had to change it so that I'm not using multiples of 90 degrees. Instead, I'm going to have to use multiples of 45 degrees because everything is compressed by 2. So if I have 3 theta, then you can probably expect that for the values of theta that I'm going to be using, well, I'm going to have to compress it by 3 times. So I'm thinking I probably have to use multiples of 30 degrees. So 0, 30, 60, 90, 120, 150, and 180, and so on and so on and so on. Now, we can go ahead and fill in the rest in a little bit, but let's just go ahead and fill in that part first for right now. Okay, so let's see. If I am doing everything correctly, then this is going to give me values of r that are either going to be equal to 0 or 8 or -8 according to what we had before. So I'm going to go ahead and plug in the first part. Let's see, 0 plugged in, 8 multiplied by the sine of 0 is equal to 0. Next, 8 multiplied by the sine of 90, so that is going to give me my first 8. Then next one, 8 multiplied by the sine of 180, that will give me 0. 8 multiplied by the sine of 270, that gives me -8. Then 8 multiplied by the sine of 360, so that gives me 0. 8 multiplied by the sine of 450, so that gives me 8. And finally, 8 multiplied by the sine of 540, which is going to give me 0. And yes, there are more. There's going to be more after this, but let's just go ahead and work with what I have right now because our plate is kind of full. Okay, first point is going to be 0, 0. So that's the pole. That's the origin right here. Let's see. Now remember, the first part is going to be a rotation from 0 to 30 degrees. So that is going to be from here all the way to here. Your radius is going to be 8 at that 30 degrees, so I'm going to go up by 8 then. So 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be this point. So in this arc over here that I just drew on the side, you're going to go from the origin to that point, which is going to be 30, 8. And remember, so as your rotation is going counterclockwise, your radius is going to increase. So that tells me your curve will probably do something like the following. Okay, so that's going to be our curve then. So it's as we increase our rotation, right, we increase our value of r. So that's going to be first piece. So that, let's go ahead and label that as, like say petal part number 1's over here. So that's going to be petal number 1. Next, afterwards, we look at what happens from 30 to 60 degrees. So that is looking at from this part all the way to this part. Your radius is going to go from 8 to 0. So that means from that point that we just went to, we're now going to go back to the origin. So the rotation is from 30 degrees to 60 degrees. So that means we're now graphing within this arc that I just drew. Well, that looks to me like it's going to be probably something like the following then. Okay, so you can see the curvature go in this way, right? So there's going to be the creation of one petal that we just created. So that's going to be like the curve number 2 then. Okay, so here is number 2, and then this part is number 2. Okay. Next piece. Now we are looking at 60 to 90 degrees, where your radius is going to be negative. So here again is 60 to 90, but we're not graphing in this portion. We're graphing in the vertical angle portion. So that is going to be from 240 to 270. Okay. The coordinate 90, -8. So that's going to be the same thing as going in a 270 direction. So 1, 2, 3, 4, 5, 6. Lost count. 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be over here. So if you're not graphing quadrant 1 and you're graphing the opposite part, you're going to this point. So my guess is that your curve must be going outward like so. So it's going to go out and then it's going to curl in to the point that you're going to want to go to. Okay, so over here, and over here. So that is going to be kind of like the curve number 3, which is this part. You can probably predict what's going to happen afterwards, right? Curve number 4 from 90 to 120 degrees, we are now going to go back to the origin because your radius is equal to 0 at 120 degrees then. So from 90 to 120, your radius is negative. So that means we're graphing again in the vertical angle part. So 270 to 360 to 300. So we're going to go ahead and curve in this way and go back to now the origin. So here is the path for it. And again, I'm just going to go ahead and label that as curve number 4 right here. Okay. Let's see, from 120 to 150. Okay, so 120 to 150, we'll call that curve number 5. And this time, you are going to use a positive radius. So from 120 to 150, let's see, 150, 8. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be somewhere up here. In this region, I'm going to graph the positive radius. So we're going to go ahead and curl out this way. So that is going to be curve number 5. And I think you guys can probably see it. Curve number 6 is probably going to be somewhere down here. Where it's going to look something like this then. Okay, so that is going to be our path, and that right there is actually going to be our curve. Now, unlike the previous problem over here where we have r is equal to 8 cosine 2 theta, it turns out, and just to save you a little bit of time, that from 180 to 360, you're just going to go back in the same path of 1, 2, 3, 4, 5, and 6 to curve. So that means that we actually can end it right here because we drew the entire graph already. The question is then, well, how do you know how many curve you have, and how do you know when that's going to happen? The best way I can tell you is that in order to figure out how do you know when to end, you just have to create the chart. So that means you just keep drawing it, and then you notice that when you start duplicating again, you can go ahead and stop. But there is something that we can depend on. For our general case of equation where you have r is equal to a cosine of b theta, the number of petals is actually determined by what b is equal to. Okay, so the number of petals is actually dependent on what b is equal to. Here you can see that when we have a sine of 3 theta, we have 3 petals. Okay, but in the case of cosine of 2 theta, we have 4 petals. Okay. And the way it works is that depending on what b is equal to, right? If b is odd, then you will have b number of petals. So that means that, that number 3 right there tells me that there are going to be 3 petals then. But whereas the other case is if b is even, okay, then, and this is the part that is a little strange, you have a 2b number of petals. So for example, if I were to ask you what is 5 multiplied by the sine of 5 theta, then that means that we're going to have 5 petals then for our graph. And in order to figure out where the locations of those petals are, you're going to have to create a chart. But whereas if I have something like, say, 2 multiplied by the cosine of 6 theta, then that means we're actually going to have 12 petals because it's going to be double 6 since b is even number, and that is going to be kind of like a really hectic case. So we're probably not going to do something like that then. Okay. All right. So hopefully the petal thing is not too bad. It gets a little grindy at first, but once you get used to it and you get adjusted, then you get the idea as to how this actually all works out. Okay, now let's go ahead and look at the last case. This is called the Lemniscate. I think there's an extra I in there actually. So let me just go ahead. Actually, Lemniscate. So I think I probably wrote it wrong. So let me go ahead and erase this word over here. Lemniscate. Okay. Anyhow, so this is the last type of curve that we're going to be looking at for polar. R squared is equal to 25 cosine of theta. And I want to know how the graph actually looks like if your if your term is going to be squared then. Okay. So let's see. Let's go ahead and do the following. Oh, actually, I think I kind of messed up on this one. So actually, let me come back to that for the time being. Let me do this example, actually, and I'll go back to the other one in a little bit. Here, let's go ahead and look at r is equal to 10 times cosine of theta over 2. Basically, the idea is that if your value of, if your inside argument is not going to be a nice number, okay? So if your inside argument is not going to be a nice number, like say 2 theta, 3 theta, but instead it's like theta over 2 or theta over 3 or something, what happens to the graph? Let's start by creating a chart, just like we did, okay? So here is theta, and then here is r. And now the values of theta, and in fact, I think this is definitely a better example to start on because it's actually similar to what we just did earlier. You would think that, it's going to be similar to that of the rose petal because, the format of this equation falls into that. But it turns out that it actually doesn't. In fact, it's far from it. So let's go ahead and use values of theta. So to figure out what r is equal to. The values of theta that we're going to use, again, giving us, normally we choose 0, 90, 180, 270, and 360. Because of the theta over 2, the values of theta that I'm going to use is going to be double that then because it's going to be an expansion. So that is to say I'm using 0, 180, 270, 360, and then we have 540, and then we have finally 630. Sorry, messed up. Let me go ahead and erase this guy. Sorry about that. I can't math because I suck at it. Let's see, 180, 360. Then we have 180 more, so that is equal to, wow, I'm just having a really bad brain fart right now. 540. And then finally 720, because all of these values, when we divide by 2, then that's going to give us the 90 degrees, multiples of 90s that we're looking for. Okay, so let's go ahead and fill it in. Let's see, first we have 10 multiplied by the cosine of 0, so that is going to give us 10 then. The next part, we have 10 multiplied by the cosine of 90 degrees, because 180 is divided by 2, so that's going to give us 0. Next, we have 10 multiplied by the cosine of 180 degrees. Then that's going to give us negative 10. Then we have 10 cosine of 270. That gives us 0. And finally, 10 multiplied by the cosine of 360 degrees. So that's going to give us 10. Let's go ahead and work with this interval. See how that works out. From 0 to 180, now this is going to be really hard because we're going to take a really big arc. We're looking at now the entire quadrant 1 to quadrant 2. Okay, so from 0 to 180, first we start at 0, 10, so that's going to be over here. 180, 0, that is again going to be the pole. Remember, you have to actually cover the entire quadrant 1 to quadrant 2 in order to go from the radius of 10 to 0. Now, again, if it helps out, let me go ahead and sneak in 90 degrees just to show you what's actually happening. At 90 degree, you're going to get R is equal to 10 multiplied by the cosine of 90 divided by 2. So that's 10 multiplied by the cosine of 45. So that is 10 multiplied by root 2 over 2. So the answer there is 5 root 2. So the coordinate over there, that's approximately like 7, which is located over here. With those 3 points, I think we have a better idea as to what's actually happening. So it turns out that the curvature of this is also going to be kind of like the limosome, because you're going to have to curl inward, right, to this point at 90 degree. And then from there, from 90 degree to 180 degrees, you curl now inward into the origin like so. Okay, so that is going to be the first part of the curvature. So it curls inward. Then the next part, from 180 to 360 degrees. So that now means we're going to look at quadrant 3 going all the way to quadrant 4. But what's tricky is we're not really graphing in quadrant 3 or quadrant 4 because, look, your radius is going from 0 to negative 10. So that means that we're going to graph in the opposite direction. Rather than graphing in quadrant 3, we're going to be graphing in quadrant 1 for the first part. And just like before, if I sneak in 270 degrees, I am pretty sure that is going to give me an R value that is going to be the negative of 5 root 2, what we just came up with earlier. So that is going to go back to this point over here. So as a result, actually, let me just kind of write that out so you can see it. When theta is equal to 270 degrees, we have R is equal to 10 multiplied by the cosine of 270 divided by 2. So that's 10 multiplied by the cosine of 135. So that's 10 times root 2 over 2, but negative. So that's negative 5 root 2. So that's how we can tell that it's going to go back to the same point. But again, we're not graphing in quadrant 3. We're graphing in quadrant 1 because the radius is negative. So that tells me that we're going to curl back up to this point over here, right? And just like what we said about the limosome, right? It's kind of like creating that hemorrhoid shape where it curls inward and then curls back out to create like a small little loop over there, a loop inside the loop. After that, from 270 to 360, that's where we're going to have a negative radius. So again, we're not going to graph in here, but instead we're going to graph in quadrant 2. We are going to go to 360 comma negative 10. So that is going to be somewhere out here like this then. So then the curve is going to look something like the following. Okay, so it's going to go out this way then as a result. Okay. Now, if we go from 360 to 540, let me kind of erase some of this stuff so then that way it's not like, all in the way. Okay, so let's go ahead and get rid of all this guy. And let me go ahead and also get rid of this too, just so that we can kind of like, draw anew. So Usually when you have so many things on there, it's actually not a good thing. So, I mean, yeah, that's how I want to kind of clear it up a little bit if I can. Oh, but one thing I do want to point out, right, the curve, right, the curvature, right, the path of the curve. So this right here, that is going to be your first curve, and then this is going to be your second curve, and then this is going to be your third curve, and then this is going to be your fourth curve. Okay, so let's now look again from 360 to 540. From 360 to 540, that's the same thing as saying quadrant 1 and quadrant 2 once again. So that means we're going to be looking at this part right here. But you are going to have radii that are going to be negative because it's negative 10 all the way to 0. So from this point, you're going to have to go to the origin, which is the pole once again. So let's see, sneaking in 450 degrees for theta, just like we did before, right? So if theta is equal to 450, then we have 10 multiplied by the cosine of 450 divided by 2. So 10 multiplied by the cosine of 225. And so 10 multiplied by negative root 2 over 2. So that's going to give us negative 5 root 2. So let's see, this coordinate right here, 450 comma negative 5 root 2. Let's see, 450 degrees, that is the same thing as 90, but in the opposite direction. So that means we're going in the 270 direction, and then 5 root 2 then. So that's going to be approximately right here then, okay? So I think that kind of works out because from 360 to 450, that is located right here, right here. But because of the vertical angle, then that means we're going to graph in quadrant 3 then. So the curve is going to go inward, okay? And then it's going to go back to that loop just like what we have over here, right? So you can see now curve number 5. And I think you can kind of see what's actually happening then. What's happening underneath in quadrant 3 and quadrant 4 is going to mimic what's happening above in quadrant 1 and quadrant 2. So without further ado and wasting the time, I'm pretty sure that the curve is probably going to go inward to the pole, and then from the pole back out to that point, which is going to be, let's see, 630 degrees, comma 5 root 2. And then finally come back out this way to the original point, which is going to be 0, comma 10 or 720, comma 10. So in terms of location or like the path of it, so here's 5, and then here is going to be 6, and then here is going to be 7, and then finally the last part is going to be 8. So this is definitely going to be our freakiest graph of yet. So here's 6, and then here's 7, and then here's 8. So it's kind of like a double limesone as a result. So that's where they got the name Lemniscate. Okay. So let's see if we can take care of this last example over here, where we have r squared is equal to 25 cosine of theta. Now, when I create the chart for this one, I think I'm going to have to make this a little bit more unique if possible, okay? Let me go ahead and take it one piece at a time, and I'm going to go ahead and, in order to compensate for the r squared, I'm going to go ahead and make 3 columns, okay? So yes, I'm still going to go ahead and choose values of theta, and fortunately, because there's no argument inside with the theta, then that means we don't have to look at anything but the multiples of 90s. So 0, 90, 180, 270, and then 360. And now for the next part, the next column, I'm going to go ahead and write 25 cosine of theta, which normally I would write r, but because we're doing r squared, right, then that means that if I want to solve for r, I'm going to have to take the square root of it. So that's why I want to create that third column for the sake of r. Okay, so here we go. Let's see. 0 plugged in, 25 cosine of 0, that's going to give us 25. Next, you're going to have, let's see, 0 you plug in, 90 when you plug it in, you're going to have 25 times the cosine of 90, which is the same thing as 0, so that is going to be nice and clean. At 180, you're going to get negative 25. Then we're going to have 0, and then we're going to have positive 25 once again. Okay, so that's just, the easier part. Now, those are the r squared value. I want to know what are the r values for each one of these because I want to know what's the radius. Well, if r squared is equal to 25, then r, now this is where it gets tricky, is going to be then equal to plus or minus 5. Okay, because remember, writing it on the side, r squared is equal to 25. We get r is equal to plus or minus 5. When we have 0, that's just plain old 0, so that's nice. Negative 25, well, that's where we run into complication because we don't want to deal with imaginary numbers right now. So, polars and imaginary, let's just kind of stay away from it for the time being because it's not used in this section. So that means to me that it's going to be does not exist. Okay, so D and E for does not exist. Or undefined, whatever you want to call it. At 0, once again, you're going to get 0. And then at 25, you're going to get plus or minus 5. Okay, let's put it all together. Okay, 0, comma, radius of 5, or 0, comma, negative 5. So how does that actually work out? Well, the way it works is you have 0, 5, which is over here, but then you also have 0, negative 5, which is located over here. So that means that you actually have two starting points. You have this right here, you starting point number 1. And over here, we have starting point number 2. Okay, so that's this freaky part because of the nature of this equation. As theta goes from 0 to 90 degrees, you're going to decrease your value of r from 5 to 0, or increase it from negative 5 to 0. So here in the first part, right, from 0 to 90 degrees, first of all, let's go ahead and pull out that point, 90, 0. So that means that's the pole once again. In quadrant 1, in order for you to go from starting point number 2 to the origin, 1 must go inward like this then as a result. Okay, and so for the other part, if you're starting at starting point number 2, where your radius is negative, you're not graphing in quadrant 1, you're graphing in quadrant 2. So that means you're probably going to do something that's symmetric. So that's going to be something like this then. Okay, so this point is going to go inward, inward, inward to the origin. And then this point is going to go inward, inward, inward into the origin. So it's kind of like creating like an S-shaped spiral. Next, from 90 to 180 degrees. Now, we don't actually graph anything there because the radii are, the r squared values are going to be negative. So therefore, we cannot take the square root of it. So quadrant 2 to quadrant 3, this part does not exist. So does not exist. We don't have to worry about that. Now from 180 to 270, I do believe that's the same thing because again, your radii are still going to be negative. So this part is going to be negative as well. So it does not exist. So here, let me just kind of write that out. DNE means does not exist. And that notation you can probably see quite a bit once you hit calculus next year. Okay, so that actually makes the graph a lot easier because that tells me now we only have that one last part to think about. 270, 0, so that's going to be the origin, right? And we're going to go from there to quadrant to 360. So that is normally quadrant 4. So again, let me just go ahead and erase what I have for right now. Okay, so that's this guy and this guy. As I said, we're going to be located in quadrant 4. And because your radii are going to be either positive or negative, then you're going to be graphing quadrant 4 or quadrant 2. You can probably suspect what's going to happen then. Let's go ahead and find those points where you're supposed to go to. 360, which is going to be 5 or negative 5. So that tells me you're going to go back to those two starting points that you have. Well, if it's anything like we just did before, then from the origin, you're going to break off into two paths. One going out this way into quadrant 2, going back into the point that you had started with in quadrant 1 and starting point number 1. And the other one is going to be the other point, which is over here, and that's going to curl back into starting point number 2. So that is going to be a curve, and yeah, so that is going to be our graph then. Okay. Let's, just writing down the path just like before. So I can kind of treat this as like path number 1, and actually this one will be path number 1 as well, because remember, this is simultaneously doing the same thing. Whereas this guy right here will then be path number 2 and also path number 2 as well. Okay. All right, so I think that'll cover everything. Thank you again for listening, and I will see you next time.